you are actually able to pass the
Right.
test.
Well, what I'm going to do with that is you have to still pass the new material. If somebody just bombed out on the previous material, in fact, the way I've done it with my evening class, and I've thought about doing it with this class too, and the only reason I didn't do it with this class was because the department head over here said you have to make it a cumulative final. That's what they told me, you have to make it cumulative. I would be inclined to say that you could just skip those parts for the test you've already, but you can't because the department said you have to make it a cumulative. But what I will do is that if you got a 0 on the cumulative part and still passed the other part, you would pass the class because you've already, that would be your big 70 conditional that you've already passed with the other ones. And so all you really have to do to minimally pass the class is just focus on the new material, make sure you know that, and you'll pass.
Okay.
So half of our material is going to be test 4.
Yeah, about half. Because we have 2 problems from each of the 3 previous tests and 6 from the new stuff. And it all comes out of the problems that I've given in the 4 days of lab problem writing in the review, review writing in the lab.
I guess when we focus more on test 4 review problems, like the what we gave us a minute.
Yeah, and that'd probably be the better focus. And
then if we have time, we can go back and review
right,
it.
right, and to get the highest grade, you're going to want to show that. I mean, a person could get a C or maybe even a B without doing well on the cumulative part, but probably to get an A, someone's going to have to do at least decent on the cumulative part. And what I'll do for the cumulative part, there'll be 2 questions. One's going to probably be a lesser calculation question. The other's going to be a more difficult problem. You'll have to get 50% credit for those, and that doesn't mean that you can get the easy problem and, okay, I've got test 1 because that's 50% of the problems. That they're not going to be weighted equally. You have to show, I'd imagine that the smaller problem might be worth 1/4 or at most 1/2 of what the larger would be, so you'd have to show some kind of, something with the larger problem. So you want to be able to, if you're focusing on one of those tests, you want to be able to do something other than the more quick calculation ones. Other questions about what to expect on the test?
What if you do good, like, on the cumulative part, but you're not getting all the new stuff? Like, can you still pass if you do good on the old stuff?
On the old stuff, but not on the new stuff.
And you do okay on the new stuff, but
right.
better on the old stuff?
And you might even pass with better than a C if you did that. I mean, typically the cutoff for making an unconditional 70 has been right around 50%. Sometimes a little bit lower. So if you got roughly half the new stuff, in fact, I kind of take it that I'm going to make 50% be the cutoff, and at the most, I mean, at the least. It might go lower than that for the 70 with that, but you know that if you get 50%, you're going to at the very least make 70 on the test, but probably higher than that. Okay, are there individual questions that are priorities for anybody to want to take a look at? Which one? The new stuff? The new stuff?
Yeah, we do go over the 12 of them.
Yeah, you should start with the hard one.
Okay.
So you start with one and work our way to the next. Yes. If you could.
Work out the more longer math problems.
Okay. The hardest one probably on the first part is going to be the projectile motion, and that there were several of those.
Is there one with the clip on it?
Yeah.
I want to do one of those.
Okay. Does somebody actually have them written down? I mean, probably a lot of people have them written down.
Here.
Okay, thank you. I do have. Okay, this is fantastic.
Good job.
Okay. Okay. We've got a total of about 24 problems. We have, if we use the entire time, we have 160 minutes for 24 problems. No, that's about what, 6 minutes a problem, maybe 7 minutes a problem.
You can just write and not talk and I think we can make it.
Right. Well, so some of this, if I show a streamlined version of what we're trying to find. Some of these, most of these are already solved really thoroughly with the notes and all kind of extra explanation. I'm going to at the very least discuss extra comments and relating it to other things for the most part. Okay, so the first one, find in polar form when you get to y max over 2 the second time. Okay, a better pen down here. Okay, the second time you get to y max over 2. Or y max over 3, so we want the vector the second time you get there, and in polar form, and you start off with a velocity vector of 60 at 50 degrees. So 60 at 50 degrees. Probably the best thing to do is to get the x and y components, which you would get dx initial, and then this is initial, would be just 60, r cosine of the angle, so 60 at cosine 50 degrees, and you get your initial y. And again, I'm skipping a lot of steps that I showed before, but those are in the notes, and this is the review, not the initial presentation, so that's a lot more appropriate. So let's just get some numbers for these.
38.77.
Okay, so 38 points, let's make it 0.6 to make it easier, and what's the other one?
It's 45.96.
40, so we'll warm it to 46, thanks. Okay, so that's close enough, we'll make our job a little bit easier. So 46. Okay, y max over 3 the second time. Well, we have to know what y max is, and we have to find the time when it gets to y max, and you get that by setting the y velocity equation equal to 0, and that's 46 minus 10t. So when that goes to 0, you have 10t is equal to 46. Our t is equal to 4.6. This thing is rising for 4.6 seconds. And this is just the equation, it's in the notes, initial velocity plus at for any direction. So we have how long it takes to get there. So we get our y position equation. It starts off at 0, so it's just going to be 46t minus 10t squared over 2. So we'd have 46t minus 5t squared. And we want to find out where it is at its maximum value, so we just put in the value of 4.6, and we get this. And an interesting thing to look at is that if you take just this term and cut it in half, it's going to be the same answer as if you do the whole expression. It's interesting that it works out that way. It works out that way in every case. I haven't looked at the exact mathematical reason why it does it, but I'm sure you could show algebraically why it does that. And so we get about 105.8. Okay, so that's our y max value. So y max over 3, we just divide that by 3. And we want to know when it gets to about 35.3. That's going to be our y max value. But you know what? If we're just looking for the polar form of the vector, there's another way we could do this. Let's just go through it this way. The other way might be a little bit easier, but this is also a way that's going to work for us. Yeah, about 35.2666 forever, so 35.3.
From what?
Where'd you get that?
Divided by 3.
Oh yeah, I'm sorry, yeah, this is y max divided by 3. That makes no sense to say that it's y max because it's not y max unless one number can be the same, can be two different numbers at the same time, and that's mathematics I haven't heard about. It'd be interesting if one number could be the same number two different ways. Okay, so we want the overall vector. Well, we need the velocity vector. That's what we're looking for, and we want its magnitude, and that's going to be vx squared plus vy squared, and we want its direction. Well, vx squared is just going to be, vx is going to still be the same. It doesn't change in this problem, so that's 38.6. 0.6. So we need Vy. And in fact, we can get Vy without having to get, we needed to have y max over 3, so that's not useless to us. We needed that value, but we have at least two ways of getting Vy. One way would be to do V final squared is equal to V initial squared plus 2ay. That's one possibility. The other is to just is to find the time when it gets to y max over 3 by using the quadratic equation and solving for it. In this case, well, we know that the initial velocity is 46. A would be -10, and y would be 35.3. This should get us the same answer as if we did all the quadratic equation to come up with the result. Let's see what this gets us here.
Another way, you're gonna have plus or minus signs.
So we have,
You can have plus or minus signs because you're doing square root of each one.
now I'm coming up with a negative number here. And
Is that
that's,
46 under the VI squared?
Yes.
yeah, it should be squared. I'm coming up with a negative number, which doesn't make any sense.
Would it be a minus 2a?
Did you square 46?
Wait, did you square 46?
Yeah, you had square.
Square 46, and then,
It's 2,000.
yeah, 21 ones, yeah, 16.
And then 2
I did
minus
the
minus
seven.
six.
and it came out to
Minus
-35.
Yeah, so that's,
Yeah, we're not doing that.
That's positive number.
oh yeah, it actually is. I typed in, okay,
Yeah, it's 282.
yeah, so this one,
Because they would be,
So it'll be 1410 and then
Yeah.
you square root it.
I'm still getting a negative number with this for some reason.
It should be 37.55.
So you're getting about 37.5, and that looks reasonable.
And it should be VF equals plus or minus 37.55.
Okay,
You take the
okay.
plus sign.
Okay, so we do this, and that looks about what we would expect. It's not, and we're going to use that it's going downward, but we really just need the magnitude here. So that's what our Vy is at that point. This is a lot easier than solving the quadratic equation. A lot less time consuming, a lot less tedious. So we can immediately get our value by just working this through, and we'll get the magnitude. Then we can get the polar form very quickly as well. I'm getting about 53.8. So the magnitude's not quite back up to what it was when it started. If it was, that would be a clue that something wasn't right.
Why did you use 38.6? How do you know that one?
Yeah, that's the initial. Remember, to get the overall, the vector is composed of two components. It has its Vx component, and now its Vy is heading down. And Vx has stayed the same. It always remains 38.6.
Okay.
There's no acceleration in the x direction. Okay, now we know it's going to be downward like this. So what we can do is, well, we can find the tangent of the inverse tangent of 37.5 over 38.6, and subtract that from 360, and we're going to get the value that we need. And I'm getting about 44, for this angle, about 44.2 degrees. And so we're looking at a positive x-axis centered about the object, so we're going to go backwards from 360. So the angle's going to be 360 minus 44.2, and what that's going to be 315.8 degrees. That's the angle. So we have the velocity vector at that time we're asking about is 53.8 and 315.8 degrees. Okay, questions over this one? It's kind of going through very quickly, but the more details are given in the notes when we first solved it. Okay, so some of the ones are going to go really, really quickly, but this is not one of the ones. In fact, what do I have, 3 or 4? Did I get, wow, I gave 4 of these problems with the projectiles. Wow, that's quite a few, but it is good to practice those because there will be a projectile problem on the test. There will be blood. So I saw that last night, so it doesn't really, I don't anticipate blood here unless, well, I don't anticipate blood here. Okay. Okay, so we're going to want to find out what, wow, how far this thing has gone, the total distance that it travels, and it goes like this, and how long it's in the air, and the velocity just before it hits in polar form.
This is number 2.
Yeah, this is number 2. A very long problem. It's doable. I'm just trying. Okay, it's imminently doable. Just okay. So okay. Okay. So x max. In other words, we need x of t, but we want, and we know that our x of t equation is just going to be vx times t. In this case, there's no acceleration. Our initial position is 0. So always a good thing to do is to get your velocity equation 60 and 40 degrees and 60 and sine of 40 degrees respectively to get Vx initial and Vy initial. So we'll get those, and then we'll solve this thing.
38.6 and 46.
Okay, so 38.6, and what's the other one? 46. 46 again.
Yeah.
Oh, interesting. Okay, thanks. Oh yeah, because the sine and cosine have that kind of inverse relationship type of thing. Not 46 degrees. Okay, so we have our x position equation. We want to know how far it goes, and so all we need to do is find out, we need t to solve for that. We're looking for how far it goes. We need to know how long it's in the air, and we can get that by setting up our y position equation, finding out how far it's gone down, and solving for t from that. So let's do that. Okay, so we have, so our y position equation, now that we have the 46 over there, it's just 46t minus 5t squared. But we have a specific value of that given to us. It drops a total of 100 meters. So our y of t, we know that y of t at the time that we need is equal to minus 100. And that's equal to 46t minus 5t squared over 2. Well, we can put, well, not 5, it's 10t squared over 2, or it's just 5t squared. We can put this into quadratic form. We can add this to both sides. So we get 5t squared minus 46t minus 100. That goes to 0. Then all we have to do is to solve the quadratic equation. There should be 2 answers. One's going to actually be a negative time that if we imagine it heading back this direction, the negative time would say if it did travel that direction, that's when it would have been there if it started right there before. 2 times, one's going to be positive, that's going to give us a time here.
It's 9.8.
Okay, so 9.8 seconds. Okay, thanks. Okay, so we have 9.8 seconds.
Hold on, time out really quick, I'm sorry.
Going back here to the beginning, this
Yeah.
60 times cosine of 40.
Right.
60 times cosine of 40, I'm getting 45, I'm getting 46 there at the cosine. So that would make differences over there.
Okay,
Yeah, I'm getting 46 also.
And
For
then the bottom number should be 38.6.
oh, so these are actually reversed.
Yes, because that would make differences over
That,
there.
that does make a difference. Okay. Yeah, they are indeed reversed. And so with that reversal there, of course, you just switch the numbers around,
That's the one.
and then we would have over here the 38.6, and would have right here again, all the way down, 38.6.
That still comes out at 9.8.
Okay, cool. So we have 9.8 seconds. We have our time. So to find x max is now just putting it into our equation. And so we just have x at 9.8 is 38.6 times 9.8, which is a number. No, it's a vegetable. Yeah, of course it's a number. And so we have about 378.28. Okay, so that was the first question. To get to the other questions, well, we've already determined how long it's in the air, that we had to solve that in the process of getting to this point. That was a result of, so the time that it's in the air is 9.8 seconds. And our x max value is this value, the furthest distance that it traveled away from where it started. Its velocity just before it hits the paper. Okay, the ground. Again, we go through the same type of a thing. We get its magnitude in this way, so we have, again, 38.6 that we're squaring, and now we still need Vy. And we can get, again, the V final Y squared.
Shouldn't that be 46, not 38.6? For that one and for the...
Yeah, it should be, okay, it should be, so, okay, so, you can get your own number here. That reminds me of a Willie Nelson song, Mr. Music Executive, write your own damn song. Write your own number there now. Yeah, it's not quite what it was, but it's a bit more.
Can we just change it over here,
Oh, yeah,
instead of the
sure.
arrows? Because I think that
Okay, yeah,
causing more
let's do that then.
issues.
Okay, so this is 46 right here, and this is 38.6, and this is 46t. Okay.
Thank you.
Oh, sure. Okay, so any other questions so far up to this point?
Oh, and that's 450.8.
450.8, thank you. Okay, so let's get 450.8 here. And now let's see, we have, so all we need is the Vy component, and we need it at the final time. And we can do our same equation as we did before. Yeah, indeed, this is 46. It's easy for the error to propagate, unfortunately. Okay, okay, so our final, this is what we need. Initially, we had 38.6, and we're going to square it, plus 2 minus 10, and then we have y is minus 100. At some point, it's going to go. It's going to give us. Well, you know, we already have the final time, so we can do it even more simply than that. We know at 9.8 seconds, and we have our Vy velocity equation is 38.6 minus 10t. So we have 38.6 minus 10 times 9.8, so that's minus 98. And we end up with 59.4 in the negative direction as our Vy when it hits the ground. So we can get our overall velocity vector now by doing this multiplication here. And again, we can include the minus sign in here, but square it, and it'll be a positive number again because the magnitude is always a positive number. Its direction, which is what we usually associate with the negative number, is taken care of by that angle. And so let's get this number, it's about 75. So about 75.1 meters per second, that's its magnitude. And then finally, for the angle, again, it's going to be in the fourth quadrant, it's heading down. It looks something like this. This side has a magnitude of 59.4, this side has one of 46. We get this angle and subtract it from 360 to get the distance that it is away from the positive x-axis. So we're going to have 360 minus the inverse tangent of 59.4 over 46. And that should get us the value that we need for this problem. Okay, I'm getting about 307.75, so let's make that about 308. So it's approximately 308. So we have our overall velocity vector is 75.1 at 308 degrees. Okay, are there questions now about this one? Okay, I know we're going through these really fast, but then we have a long ways to go, and there are examples.
We got.
Okay, that's cool. Just reminding about that. We know we have limited time here, so, okay.
We'll let you know if we get lost.
Okay. I've sometimes given a chance before the exam to ask questions on the day of the exam, but we only have such a small amount of time when we get here for the exam. We have to hit the ground running with that too. Okay, so, okay, this next one, well, let's get it done here. Okay, so the next one, we have, we're going upward, 50 degrees, 30 is the magnitude, it's going like this. We know that at some point, this thing is going to fall 70 meters, no initial velocity, and it's at 0.08, it's at 0.8 of x max. That's where it's going to fall from. And so when should the mass be dropped relative to the projectile so that they will collide? Okay, what we have to do is we have to find out how far this mass travels. We want to find out what distance it travels to get here, how long it takes it to drop there, and where exactly it coincides, and how long into the process it takes place for this one. To do that, we're going to have to find what y max is when x max is 0.8 of its final value. So we're going to have to find out, well, we need the y value. Well, we need the time when this gets here. If we look at this, we can call it projectile A. Its equation of motion, it's going to go this distance d. It's going to go a distance d in at squared. If we count downward as the negative direction for this and count gravity as 10 meters per second squared, it's going in what we can designate as a positive direction of distance d. So we could say, okay, and that should be over 2. So it's going to equal to 10 over 2 p squared. That's the distance that it falls. So 5p squared is equal to the distance that it falls. We can find out how long it takes to drop that distance and coordinate its time with this projectiles if we know that. So we have to find the distance that it falls. And the distance that it's going to fall is going to be y when x is equal to 0.8 x max. So it's going to be, this distance will be 70 minus, we'll call this point y2 or something of that nature. So it's 70 minus y2. If this distance here, from here to here is y2, 70 minus y2 is the distance that thing falls. Okay, so we have to find y2. So what we have is we have 5p squared is equal to 70 minus y2. Well, y2 is equal to y at the time t when x is equal to 0.8 x max. So we have to find out when x is, so we have to find out what 0.8 of how long this thing is in the air. We can get that. And then use that to find the height for the y. So again, in almost all situations like this, we have to get Vx, which again is 30 cosine 50 degrees, and we have Vy, initial, is 30 sine of 50 degrees. And so we have to get those. Once we have those, it becomes possible. Okay. Okay, so I'm getting about 19.3 here.
30 sine of 50 is 22.98.
22.9, okay, so let's make that 23, thanks. Okay, so we have Vx and Vy, we want to find out 0.8 x max. Well, our x equation is 19.3 t, but we really need to find out how long this thing is in the air. One way we can do it is we can say, okay, our y velocity equation is 23 minus 10t. And we know that, I haven't emphasized this, but I'll mention it now, it's a really good shortcut for this one. When you're starting to go up, the y velocity is in this direction at 23 meters per second. When it hits the ground, it's going the opposite direction at 23 meters per second. And so we know that at the time when it hits the ground, it's at minus 23. So minus 23 is equal to 23 minus 10t. So we have minus 46 is equal to minus 10t. So the time in flight is 4.6. Well, x is directly proportional to that, so x is going to be 0.8 of its value when you've moved, when 0.8 of the time has gone by. So 0.8 t is equal to 0.8 times 4.6, so that should be what, 3.68. So we have about 3.68 seconds. So we're going to get our y2 value by using this. So our y position equation, we have our initial velocity, which is 23. So we have 23t minus 5t squared. So our y position at that time we can get it that way. I'm getting about 42.3. So it's about 42.3. That's the one that we call y2 over here. So that means the projectile itself, I mean, what it's going to collide with, so what this tells us is that the distance is equal to 70 minus this 42.3, and that's equal, or relating it back to this equation here, that's equal to 5t squared. So this will get us, what, 27.7 is equal to 5t squared. Divided through by 5, we're going to get what? 5.44. Is it 44? Well, it's approximately 5.4. Then there's going to be what? 5.5414. So we'll keep it at that. And we square root both sides. And we'll take the positive value. We're not going to deal in negative time. And I'm getting about 2.32 seconds. Okay, so now what we know is to fall from here to here, it takes this object 2.32 seconds. And we know to get to that point, this object takes a total of 3.68 seconds. So how much before do we need to, so the question was, when should the mass be dropped relative to the time the projectile is fired? Okay, so if we take that 3.68.
Okay, I'm sorry.
I think
I'm
that
sorry.
42.3 is actually 16.85 or 16.
Oh, is it? Okay.
Yeah, we got 16.9.
16.9, really? Okay.
Because 23 times 3.68 is 84.64, and then 3.68 squared is 13.54. Multiply that by 5 gives us 67.712. And when you do the subtractions there, I think did it out long ways just to make sure.
Right.
Yeah, it should be 16.9.
Yeah, it's 16.9. I'm not sure. Okay, 16.9. Okay, so we'll say 16.9, and then, okay, thank you. So let's get this going here again. 16.9, so we're gonna have 53.1, is it? Okay, and then we divide that through by 5, you get about 10.6. 10.6, and then
Two.
what's it, 2, okay. And then, somebody have a value for what the time actually is then?
3.25.
Okay, about 3.25, 26 maybe?
Yeah, it's
Okay.
2.6.
Okay, so, okay, and so the difference between this is, what is that, 0.42 seconds. So that means we have to, if we drop it 0.42 seconds after we fire the projectile, they should collide, assuming there isn't too much friction with the wind. That reminds me that somehow they got the calculations off or something that I read yesterday, how the Mythbusters guys fired a cannonball and it escaped from their area and tore through a house, or when people were sleeping, tore out the back of the house and smashed into a minivan. Somebody's, nobody was hurt, but it was the first time in all the show's history that something that drastically went wrong. But that was kind of interesting. Okay, questions now about this one. Out of 1, 2, 3, and 4, only one of those will actually appear on the test.
Only one of the 4?
Yeah. In fact,
Can we start going over the new stuff?
I was going to say, I'm not going to do, in fact, 4 won't appear on there. I'll take out 4 from consideration, not number 4. If you
So
don't-
the 1, 2, and 3, only one problem will be there.
Right, only one like that,
Okay.
and then one like,
There you
like the others. Okay.
1, 2, and 3, one of them, we're good. That's it.
Right,
So
and
the
then,
new stuff.
Okay, let's do this.
well, okay, are there requests for other sections?
Well, I honestly want to go through all, as many problems as we can go through.
I know, but I wanna go through the.
Well, the new
website.
stuff is, since that's gonna be more important for us to
Yeah,
dictate.
in terms of, if you've done well in the previous test,
Well,
that's what you
that's-
have to be concerned about, right? And you have to.
You should be more worried about this.
Okay,
Since they've actually tried.
Okay, so
Okay, shall we look at the,
one of the 3 we just did.
what we could do is go back and forth, one from the new, one from an older section, go back and
No,
forth,
no,
kind
no,
of, okay,
Let's
so.
just do section 4 first, and then if that's
Okay,
not
okay,
good,
okay,
upstairs.
and you have a lot of, I mean, we did
That's fine.
extensively review the tests when we had them, that they're very much like the test problems from before.
Are they
So-
gonna be questioned the same, like as these?
Yeah, I'm gonna try to make them as close to this as possible, I'm gonna include drawings too, so that always goes a long ways, I know.
Yeah.
Okay, so we'll have drawings
Like,
for sure on
I've
this.
done myself.
Okay,
We got
okay, so
problems.
let's take a look at, we have an equilibrium system situation here.
And these are based off the new problems.
Yeah, in fact, this is, I gave 12 new problems,
This is step 4.
Tuesday.
Okay.
Okay.
And
Okay.
this is the first of those. Okay, so, we have a mass 2, and let me, finish drawing this out here. Okay, so we have mass 1 here, it was 8 centimeters from the side. Well, you'll all have the problem, well, not everybody has the problem. So, I gave the center of mass at 49 centimeters. The support was placed 41 centimeters from one side. The center of mass I gave as 49 centimeters, and I said that we had a mass 2 placed on this end over here. The mass 2 was a total of 70 centimeters from one side of the stick. And I gave the mass of the stick as 200 grams, and I gave mass 2 as 80 grams, and the idea here was to find mass 1 if this thing turns out to be in static equilibrium, which it does. And the best thing to do here, you know the sum of the torques go to 0 if you give oppositely directed torques opposite signs. And we have to pick a point to take the torque about, and it's probably best to pick it at the point where the support is. That's the point we're going to calculate all of the torques around. And so if you look at the torques that are on this thing, there's a torque due to one that's going to tend to twist it around this point in this direction. The center of mass torque will tend to twist it in this direction. We'll call that the torque from the stick, T sub S. And the torque from mass 2 will also tend to twist it in this direction. So what we can say from that is, if the sum of the torques go to 0, T1 minus TS minus T2, that goes to 0. We're looking for mass 1, so we have T1 is equal to TS plus T or tau 2. Okay, so we have this. Now we have to look at the definition of torque, which each of the individual torques is the same. Its magnitude will be RF sine of the angle. The angle is the angle that the force from that mass makes with the radial distance from the point that we're taking the torque about. And so if you look at here, there's a radial distance out from this point, and there's a force 1 from mass 1 is directed downward. The angle is 90 degrees. And in all cases, down here, the radial arm and the force downward, the radius out here and the force downward, it's always 90 degrees. So this part is going to be easy to evaluate. The sine of 90 degrees is another way of saying 1. So we've got that. So all we have to do is focus on well, it simplifies our expression. We can write out our expression now. On the one side, we have R1, F1. On the other side, we have RS, MS, where the S stands for the stick, plus R2, M2. Actually, not. I need to do, I skipped a step here, and it's not correct as I've written it. That should be the force from the stick and the force due to mass 2. And that force is going to be purely gravitational, so what we can do with that is write everything in terms of the gravitational force. And we're going to see that the gravitational constant, we can cancel that. So we end up with R1, M1 is equal to RS, MS plus R2, M2. And since we're solving for this mass here, all we got to do is divide by R of 1, and then the problem becomes making sure you determine what the R values are. What are R? Okay, we don't have to make any conversions of the R's from centimeters to meters, because any conversion factor will just cancel since we have it in the bottom and the top. And if we're going to report our mass in grams, which we're going to here, we can keep everything in terms of grams. So in this case, no conversions are necessary. Okay, so now we have to look at how we get these R values. If you look at RS, well, let's start with R1.
R1 is 8 over, so that would be 41 minus 8.
Exactly, it's that distance. So R1 is going to be
33.
It's going to be 33, and in fact, it's
Negative 33.
well, we've taken care of a negative sign by giving the oppositely directed torques opposite signs. We could have put it in there that way, but it comes out the same. We've already accounted for that by giving the oppositely directed torques opposite signs. In other words, over here.
Okay, so when we did that, when we added the sign
Right,
over.
right. I mean, we could have had this as positive, and then when we got our R's, we could have put the negative sign in there by giving the radiuses on one side negative and the other side positive, and that would have given us the same result here. But we kind of took care of that bookkeeping detail that way. Okay, so we want the distance that it is. So in other words, R is the distance away from where we're taking the torque about, which is right here, out to this point here. So it's 41 minus 8. Exactly, so we have 33. R2 is 70 minus 41, so we have 29. And RS, I said the center of mass is at 49, so it's 49 minus 1, I mean 41, so it's 8. So this will allow us to very quickly get our mass. Okay, the mass of the stick I said was 200. Okay, R2 was 8, and mass 2 we said was
80.
80, okay. And then divide that through by the R1, and we'll get a result that's gonna, what's that, 8? No, it's, R2 is actually 29. Let me get that straight here. Okay. Does somebody have a value for this mass?
Which one, R2 is which two?
R2 is the distance, this is mass 2 here, so R2 is going to be the distance from here out to here. It's from the point that we take the torque about. Yeah, 70 minus 41, which is again the 29. Guys, it's important to keep in mind what R refers to. Okay, does somebody have a value for this mass here? 118.7, okay.
Or 0.79.
118, well, let's make it 118.8, that's close enough. And we'll do a little approximation squiggly thing too, and that's gonna be in grams. Okay, any questions about this problem here? I think there's a really good chance this one's gonna be on the problem, and I have to say it that way because I haven't decided, I haven't written the test yet, that it's gonna be like these here.
The question for that, what was the question for it, like asking?
Oh, the question was, what is mass 1 if this thing is balanced? Yeah. Okay, question 2. We have to involve, okay, so we have a solid sphere, and we know two things about it. First, we know it's a solid sphere, and it's not moving at all when it begins, so it has no angular velocity. It's at the top of a hill. We don't know how high this hill is. That's what we're trying to find out. And we know that we've measured its velocity at the bottom, and it's cruising along at a speed of about 10 meters per second. And we know that its moment of inertia for this solid sphere is 2/5 mr squared. Okay, so this is question 2. And our one question here is, how high is this hill that it rolls down from, given that it's gained that much in terms of meters per second of a velocity? And here we have to go, we're saying there's going to be no friction here, so we go on the conservation of energy. And so we're going to look at, it's going to have a change in potential energy that's going to equal its change in kinetic energy. You're going to convert a certain amount of potential energy to kinetic energy. And its change in potential energy is just mgh on the one side, and that energy, as it rolls down, converts into kinetic, and so that's going to equal to our total kinetic energy on this side. But that total kinetic energy has two parts, the linear kinetic energy and the rotational kinetic energy, and we're going to have to solve it for here. We're looking for h. Okay, well, one way we can begin to simplify this expression is to put the value for the moment of inertia into the one part of the equation here. So mv squared over 2 plus 2/5 mr squared omega squared over 2. So that should give us, what, mv squared over 2. The 2 cancels the 1 up here, so we should have mr squared omega squared over 5. And we have mgh. Well, immediately we can see we can knock out that m, which is good because we don't know what the m is. And we just about have what we need. We can divide through by g, but before we do that, we're kind of stuck because we don't know the radius and we don't know what its angular velocity is at the end. Does anybody have a suggestion about getting past this impasse that is not impassable, really? Yeah.
Isn't omega is 0, so that side is crossed out?
Initially it's 0, but what we're looking at here is we're saying that I did it a little bit differently before where it was initially 0, but we're looking at its potential energy changed by the amount mgh as it went down the hill, and that was converted into the kinetic energy, which it has at the bottom. So it is spinning around. It's like a bowling ball going down a hill. Remember that there was one key result here, that we have that V is equal to R omega. And so that means V squared is equal to R squared omega squared, and we can put that into our expression, and we end up getting everything in terms of V squared. We have V squared over 2 plus V squared over 5, and we know what V is. So we can say, okay, we have 10 squared over 2 plus 10 squared over 5, and what one's going to give us 50, the other's going to give us 20. So we have 70 on the one side, GH on the other, and if we use our approximation for G as about 10, it's going to give us approximately 7 meters, yeah. The hill is about 7 meters tall. And that's it. Yeah, this one's is really a very quick calculation problem. It looks, when you first see it, it looks a lot more formidable than it is. And it's interesting because it looks like there's no way in the world you have enough information to solve this thing. But when you start putting things in, things begin to cancel. You equate velocities with other types of velocities with the right parameters, and it turns out to solve very nicely. Okay, questions about this one? Okay, we need the total energy to bring 100 grams of ice at 5 degrees Celsius. Okay, so this one's going to be, okay, so we have ice. So we start at minus 5 degrees Celsius with ice, and we want to end up with 10 degrees Celsius water. Well, two things are going to happen with this. Well, we're going to change the temperature. We need energy for that. So we need energy for temperature change, and we need energy for the phase change as it warms and goes from ice back into water. We're going to have to add energy to it to do that, to heat it up. So we have two energies. So we'll call this the energy for the temperature, and we'll call this the energy for the phase. You can call them anything you want to, or call them nothing at all and just put it in more directly. But we said that we have, the way we wrote it in class was like this, where delta Q was the energy from heat. And so we have MC delta T on the one hand, and then we said that the energy needed to bring about a phase change was dependent upon the amount of the substance and the amount of the substance. And we said we started with 100 grams of water, of ice. And so we have to have the latent heat of fusion times mass. The mass that we're looking at, that's going to be the energy for the phase change. And this will be the energy for the change in the temperature. Okay, I gave some constants for these things. I have them in my notes here too. Let me quickly recall them. Okay, so in other words, what we need to have is we need the specific heat for water, and we also need the latent heat of fusion. So in other words, what we can write is that the energy that we need to give to bring this about, the energy is going to be equal to these two things we've just started looking at that we've defined here, to keep it in that notation first. And so the energy to bring about the temperature was mc times the change in temperature, plus we had the mass times the latent heat of fusion, L sub s, for water. I'll give you that value in anything that we do here. Okay.
Are you gonna make us like your own formula sheet as well, so that we can like cross-reference?
I wasn't planning on doing that since you have the ability to do this. I can provide it.
Just because in case you write something down wrong.
Okay, yeah, but and if you do, don't worry about that, because you'll turn that in and I'll go check your formula sheet. Oh, they just made a small mistake there, and that's something that I can live with without the loss of points or anything. Okay, so if we look at the So the specific heat for water, this is just 1 calorie per gram times degrees Celsius, and the latent heat of fusion for this thing, for water, latent heat of fusion is about 80 calories per gram. Okay, so we have 80 calories per gram. So if you put in the values that we know to get this, okay, so we have 1 calorie per gram times degrees Celsius. We have a total of 100 grams of water, or of ice. The change in temperature is its final minus its initial, so its final is 10 degrees minus the -5, and be sure you put the minus in there because it'll come out incorrect if you don't. And then we have, and so this is grams, and this is degrees Celsius, so we'll be left with units of calories. Then we have 100 grams times 80 calories per gram. And so we end up with 15, so 100 times 15 is 1,500 plus 800. We have 23 calories of energy. We could easily change that over to joules. I'll give the conversion factor, and if I ask you to change it to joules, it's just a matter of having the conversion factor, which 4.184 in terms of joules per calorie, and you'll have the appropriate number of joules. So that one's intended to be a rather quick calculation question as well. Whatever substance I give you, I'll make sure you have a specific heat value for it, that letter C, and I'll make sure you have either a latent heat of vaporization or a latent heat of fusion, where vaporization would be from a liquid to gas or gas condensing back into liquid. And I'll ask you about that, something like that. But I'll give you the different constants you need.
So the formula for that one is the MC equals to T.
Right.
Okay.
Right. For the change in temperature, you have two energies two places the energy is going. One place it's going to change the temperature, and at some point the energy doesn't change the temperature, but it brings about the phase change before the temperature changes again. Okay, questions about this problem here?
So for 4.184 calories is 1 joule?
It is, yeah, I'll give you that conversion factor too.
So we need to put it in joules?
Oh, I'm going to probably ask for it in calories, but if I did, it would just be a matter of multiplying by that conversion factor, which I'll provide you as well. Okay, the next one's a little bit tricky because it deals with the shearing stress, or with the shear modulus of a material. And the way to have it set up is I'm giving you the results of an experiment, of a hypothetical experiment on, say, some kind of material, and what I gave you was you have a 6 by 8 by 3 centimeter block of a certain kind of material, but you're going to find out how it responds to shearing forces by testing it. So it looks like that initially, and then you apply a pair of shearing forces to it, they're all directed along either the top face or the bottom face, and you're going to find how that deforms the block to give you an idea of what its shearing strength is, or what its shear modulus is. And so I say if you apply 100 newtons to it, and the result of that, let's say, as a result, this is always a little bit challenging to draw here. Let's say I've exaggerated the distortion. Let's say this top face moves by 2 millimeters. That's, of course, a lot bigger than 2 millimeters would be, since this whole side is 8 centimeters. But just to show the effect, I exaggerate it. Okay, and the question is to get the shear modulus for this, and you have to remember what the different pieces of the shear modulus refer to. So you have the force, well in this case it's just the force over the area that it's shearing divided by delta x. And I forget how I gave this in class. I think I gave this maybe as an H or maybe as an L. You see it different ways. The L doesn't make any sense.
H.
H because it's more the height of the block in the way that it's usually drawn. I've seen it almost always given as L, but L would be more like the length of something, but it's whatever you define that parameter to be. It's that height of that block. It's the separation of the two surfaces that are sheared by the pair of shearing forces. Okay, so right here we know that 100 is what's acting on each of the faces that get sheared. The area that gets sheared is this top area up here, and it has an area. So the area is going to be 3 centimeters by 8 centimeters. We're going to want to convert that over to not centimeters squared, but to meters squared, because the force is in terms of newtons, and newtons has units of kilograms times meters per second squared. The delta x, we're going to, on the bottom you have a ratio. You have the initial separation distance between the two faces, so we have 2 millimeters over 8 centimeters. I'm sorry, 6 centimeters. The distance that the two were initially separated. So again, this is the distance h, and this is the distance delta x, how much the top face was removed by as a result of the application of the shearing forces. Okay, so this is a ratio, but we need to make sure they have compatible units. We don't have to convert them to meters because whatever units we use here are going to cancel away. We want to make sure that it's a meaningful ratio. So let's convert the 2 millimeters to centimeters. So millimeters to centimeters, we're going to have 0.2. So this whole bottom quantity will have 0.2 over 6. And that will give us an appropriate number. In fact, let's calculate that so we can stop writing it as 0.2 over 6 and write it as an individual number. But that's going to be 0.033. 3's going on forever. So what we get out of that is 100 over that area that we're just about to calculate divided by 0.0333. So we can rewrite that as 100 over 0.0333A. So once we have A, we essentially have our shear modulus. Questions about this so far? Okay. Okay, so again, let's get our, we have 3 times 8 is 24 centimeters squared. And the conversion factor to go from centimeters squared to meters squared, we'll have 24 times 10 to the minus 4 meters squared. Okay, and the reason we have to go to meters squared is we have the top thing as a force, and its units are newtons, which is a kilograms times meters per second squared. So if we didn't convert to meters squared, we're going to have a number that's off.
Wait, is that 3 times 8 or 3.8?
No, it's 3 times 8. So we get the 24 centimeters squared, and then we use our conversion factor to convert over to meters squared.
Wait, can I ask?
Oh yeah, for sure.
24 centimeters square over 0.03 centimeter. Wouldn't that centimeter cross out and you only get 1 centimeter?
Okay, on the bottom we have that 0.033. We got that from the ratio of delta x
Right, that's what I'm saying.
over h.
You get the centimeter out of that.
And we converted that to centimeters, and we had centimeters on the bottom. So the centimeters for the bottom part cancel. The
Right.
bottom part has no units. However, the area still has units. It has units of centimeters squared, and we have to make that compatible with the units that we have of meters up top. Otherwise, it's going to distort the results. Okay, so I should say that that is A, and that's A. So if we combine our results, we get 100 over 0.0333. And we can carry on the 3's a lot longer, but there's no point here, which it typically should be for most materials, it's going to be a really large number. This is one that yeah, I'm getting, this is a cool number right here. If you look at it, what it is, it's, unless I've done something wrong, it's 125, 125, 1.251, and my guess is that it carries out like that probably forever. That's a cool kind of number. Yes, so we get this, and that's going to be in terms of newtons per meter squared.
So you did the 3 times 8.
Right. And that was 24 centimeters squared for the area, okay. But then we have to convert that area over to meters squared to have it.
I just got 1,250,000. That's what I got.
I wonder, did
I didn't do .0333. I did 130.
Okay, yeah, and that makes a difference. And it's approximately the same, really. Although if those were dollars, you would want to make sure you had the extra $1,012.51. But yeah, so it's and I would count that as the correct answer too on the test. Rounding, the different ways of rounding, it's fine, really. Other questions about this problem?
Wait, what did you get?
I got, he got, okay. Okay, I think we might have time to do one more problem right here. We've got about 9 minutes before going upstairs, and then we'll continue doing problems until we run out of time upstairs as well. Okay, so the next one is also one of the moduluses that help to quantify how solids and also other materials respond to pressure. And in this case, we had a beam that was 8 centimeters, so not a very long beam, 8 centimeters long, and a top surface area of 7 centimeters by, did I say 8 meters or 8 centimeters? Did I get for the length on number 5?
3 meters.
3 meters. Oh, how high was this, did I guess?
3 meters.
3.
So 3 meters. Okay, so for 3 meters, okay.
You put 5, 7.
Yeah, the top was 5 centimeters, and then maybe back by about 7 centimeters, and I said, what, 3 meters?
3 meters.
Okay, okay, so 3 meters. Okay, and then we're going to add a mass to the top of this. So this is it before we add a mass to the top of it. Then if we add a mass to the top, and I'm saying we're adding 1,000,000 kilograms to the top, 10 to the 6 kilograms, we find out that it gets compressed by 2 millimeters. So that's going to be our change in the length of the object. So we're looking for the Young's modulus, or the tensile modulus, and we have the force that's directed perpendicular to the surface, to the surface that it's being directed on. Then we have the change in the dimension by the original dimension. And so this is just a matter of putting in the numbers that we have here, and again, making any appropriate conversions. Okay, so the force, that's going to be from gravity. So that's going to be just 10 to the 6th, and then we use our usual idealization of gravity as 10. Here we're going to have, again, 7 by 5. But we're going to convert it, again, the conversion from centimeters squared to meters squared, and then our delta L. Again, we're going to have to make sure that this length, it's going to be a ratio. The units will cancel on the bottom. We want to make sure that they're the same units so that the cancellation is possible. And so 2 millimeters, we want to convert that over to meters, or we can convert L over to millimeters. Either way, we can do it. So we'll do 2, and then we'll convert this over to millimeters, 3,000 millimeters. So this is meters to millimeters. Either way, you can do it. And so if we then collect all of that without the director's commentary, we can...
Don't you have to convert everything to meters, because you change meters to up top?
You might think so, but here, this is a ratio, and these two are gonna cancel. We could convert them to meters, that would be appropriate too, but, or anything, but since this one remains, it has to be compatible with that unit of meters in the force. Okay, so then we have 7.5 times 10 to the minus 4 all over 2 divided by 3,000. And this should turn out to be a fairly large number. Usually these moduluses are pretty large, and you can insert the numbers, come up with an answer, and that's what we'll leave this one,
That's 7.5.
barring any questions, and there is a question. Yeah.
Okay, you have 10 to the -4, because you're doing centimeters squared to meters squared?
Right, right.
Isn't centimeters to meters just like 2 over?
Well, see, if you look at this, 1 centimeter is equal to 0.01 meters, so 1 centimeter times 1 centimeter would be 0.01 meters times 0.01 meters, and you can see how that becomes, yeah. I remind myself of it that way sometimes too. I don't automatically just, oh yeah, it's 10 to the minus 4. If I can't think of it, I rederive it like that frequently. Okay, any other questions about this first set of problems we've done here? Okay, I think we're gonna,
for that one?
yeah, for this one, that's it. You just put the numbers in, and it's good. You're gonna end up having,
Oh, that's just
you're
the
gonna
plug-in
report
number.
it, yeah. It's gonna be in terms of newtons per meter squared. Does somebody have a result for this? Did somebody punch it in?
Well,
Something,
I'm going to it.
okay.
Is it gonna be a giant number?
It should be on the order of 10 to the 6 or greater. So sometimes a bit less, but a lot of materials mostly have really, really large numbers.
15 to the 4?
4.3, really?
Oh, times 10 to the 13.
Okay, 10 to the 13. Okay, that sounds more like what I would expect. So about 4.3 times 10 to the 13. I'm not sure anything actually has a modulus that high. Titanium, maybe, I'm not familiar enough, but that's, most have on the order of at least 10 to the 9. Okay, that's all we're going to do for down here, so I'll see you all upstairs in about 10 minutes. And we'll do as many as we have a chance to do.
Well, are we continuing from the lecture?
We are, yeah.
Okay.
So this is going to be question 6 out of the 12 new problems. Okay, so question 6, I give you a certain volume of an object that's submerged. We have 0.8 meters by dimension, and you have, going back about 0.4 meters, you have under the water 0.4 meters. The water line is about right here. And above the water, we have an additional 0.5 meters. And we have a box here that, so in other words, the total distance is 0.9 meters, the overall volume of the box. And the first question was, well, this thing's in fresh water. This is how it's floating. We have for fresh water, its density is 1,000 kilograms per cubic meter. Okay, so what we're looking at first is the mass of this box and also its density. So we'll call it the mass of the box and its density. Okay, what we know about this is the buoyant force that the water pushes up on it. It's floating, so it's exactly counteracting gravity, but it's equal to rho vg, and that's equal to the mass of the ball times gravity, of the box times gravity. In other words, it's not sinking, so gravity is pushing down, the buoyant force is pushing up. The two are equal, and we can equate them. This is the general expression for the force that the fluid, or whatever the fluid is, water or what have you, pushes up with on an object that's submerged in it. Okay, so immediately we can see that we can cancel the g. And so we have the mass of the ball is equal to the density of water times the volume of water that gets displaced. Well, again, this is just 1,000, and the volume of water that gets displaced is the volume that's actually under the water. And so you can see that its volume would be 0.8 times 0.4 let me make that more distinct what these, so we have 0.8 times 0.4 times 0.4. You can see that that's the volume of water that gets pushed out of the way for the box to come to rest there. And so we end up with, the box has a mass of 128 kilograms. Again, if you look at the units, we have kilograms per meter cubed, and we have cubic meters here. So we end up with 128 kilograms. That's the mass of the ball, of the box. And then we want the density of the box. And by the definition of density, it's just the, density is the mass per volume. So the density for the ball is the mass of the ball of the box times the volume of the box. And the overall volume of the box is larger than the volume of water that gets moved out of the way. So you have 128 over 0.8 times 0.9 times 0.4. And so that's going to give us a value for the density of the box.
So P is density?
Yeah, P is the density, and that's the mass divided by the volume. Unfortunately, the letter P is worked more than triple time in physics. You have all sorts of things: momentum,
So
pressure,
what is
power.
the P over there? Is that density of water?
Yeah, this is the density of water.
Okay.
And I'll give you, whatever fluid, like one time I did something emerged in bootleg alcohol, and I gave you the density of alcohol for a previous class. And so I do different things like that, but I'll have to give you the density of whatever fluid the object is submerged in. Okay.
424.
Oh, wow, thank you. Okay, so 444? Okay, so we'll make it about 444 kilograms per cubic meter. And notice that its density is greater than that of, is less than that of water. If it were more dense, it's not going to float. So it floats. But now the next part of our question is to get it to the point where it's not floating, to where it's just even with the water, and we're going to add some mass to it. We'll call that the added mass. So again, this is the mass of the ball. It's under the water, and we're going to find out how much mass we have to add to get it to be completely underwater. And so again, we have our buoyant force will be equal to the density of the water times the volume of water displaced times gravity. That's the force that's pushing up on this thing, and pushing down, we have gravity, but now it's going to be equal to the mass, to the two masses, both having the force of gravity. Their combined mass is pushing down. So what we equated with over here is mass A plus, it's a really weird looking M,
That's the
mass
mass
B,
of the other box.
the mass of the box, times gravity.
It's an added one.
And we're adding mass to the top to get the box to be completely underwater, not well,
So
it's
just
just top's going to be
mass
flush
added.
with the top of the water. Again, we can cancel out our gravity, and we
Should
have
the entire class with their phones out, taking pictures.
I know,
we
right?
have
That's bums.
this relationship, but we're looking for the added mass. So we're going to
You
have
know, so here, taking
we
pictures.
solve for the added
That's
mass,
smart.
and this is what we get. So let's take this over here and.
Hold on. Okay. So, no, I'm taking the picture.
Okay, we'll take this over here, but are there questions other than a request to slow down a little bit? Okay.
Good now.
Just.
Okay.
For you,
Okay, so,
I'm
well,
trying.
so the density, so the density is, again, 1,000. Now the volume is the entire volume of the box, so that's 0.8 times 0.9 times 0.4, and we subtract the mass of, that was already there, the mass of the box, and we get the added mass. And so, does somebody have a value for that?
288 minus 120.
Okay, so 288 minus 128, and so we get about 160 kilograms. If you add that to the top, and if you need me to slow down, just
You're good.
okay, cool. Okay, so let's now that we've solved that one, let's move on to number 7. Number 7. Okay, this one, we have a hydraulic system here. We have some incompressible fluid confined, and so we apply a pressure at one area, and it's going to equal to the pressure that gets exerted on all other areas. And we want to know if we applied enough, if we applied the force to it, a force that everybody can apply of 200 newtons to a small area, how much force can we apply to the larger area? And again, what we have is the force exerted on one area is going to go and be exerted at the other areas, transmitted by the incompressible fluid, and the fact that it's in a confined space. And we wanted to know how much mass could a person lift with this force that they apply if they're able to lift 20 kilograms. And so the force, we're solving for force 2 first. So we get F1 over A1 times A2. And here, the area is the area of the circle, so that's pi r squared. What's nice, the pi's will cancel in each case. So we have F2 will be, we've applied a 200 Newton force straight down. Again, a force everyone's capable of exerting. And we have pi r2 squared over pi r1 squared. The pi's will cancel, and we end up with 200 times the ratio of the squared radiuses. I've given the radiuses in terms of centimeters, and we're going to want the force in newtons, but what's nice is that we have centimeters squared at top, centimeters squared down below. We don't have to make any conversions. Any conversions would just cancel out. Okay, so in one case we have, in one case up top we have 10, so we have 10 squared or 100. In the bottom we have 2, so that's 4. So we have, what, 200 times 25, and that should be, what, 10,000. Okay, so we have, you can exert a force of 10,000 newtons if you have the work amplification device set up. So how many kilograms would this be equivalent to moving? And we're going to use the approximation, again, that gravity is equal to 10, even though we know it's not. We're going to use that approximation. I made that a little bit too large there. Okay, so...
It's 5,000.
It's 5,000, it's not 10,000.
Oh, yeah, of course, yeah, it's not, you know what I was thinking with that. How in the world did I get that? Okay, we don't need to delve into that psychology. Okay, so let's get this right here, 5,000, and you divide through by 10, and so you end up with 500 kilograms. So you go from being able to, without the use of this, being able to maybe hoist 20 kilograms, now you can do 500 kilograms.
That's it.
And that's it. It's a very quick problem. About half the questions in the second part are really very easy questions. Very, very... okay. Okay, so questions now about this one. Okay, so let's look at question A. We're looking for the total pressure on a diver 40 meters below the surface of salt water. So maybe they're diving, well, in salt water somewhere. Okay, so we have them as 40 meters below. We have a diver swimming along. Not swimming very well, it looks like, but they're swimming along. Okay, so we have 1030 kilograms per meter cubed. I'm going to have to give you the density of whatever substance that we're working with. And we're looking for the total
I
pressure.
think that was 4
And the total
centimeters.
pressure is the pressure of the atmosphere plus the hydrostatic pressure. The pressure of the atmosphere is something I'll give you, 1.01 times 10 to the 5th newtons per meter squared. And the hydrostatic pressure, that's just rho g h. Rho being the P rho, whatever it is, P rho, having that be the density of the fluid that the person is under, h, a column of that fluid, h meters in height. So all we have to do is just put in 1030 times 10 times, in this case, 40, and this will get us the total pressure. So again, this one is extraordinarily easy, and hopefully no one's going to miss this one. It's one that we're going to have about maybe three of these kinds that are pretty straightforward calculations. Okay, so I'm getting out of this one's about 4.12 times 10 to the 5th. So altogether we have about 5.13 times 10 to the 5th newtons per meter squared, or that's sometimes called a Pascal. Okay.
And that's it?
And that's it,
That's
yeah.
it?
Yeah, so many of these
We have them all like that.
are really very easy. Okay. Okay, so let's look at now question 9. The average velocity of helium, positive 2 charge helium, in space. So we're going to use, we know what the average temperature in space is. It's about 3.5 Kelvin, so that's the temperature the helium's in. We're looking at the helium positive 2 atom. So it has 4 nucleons, 2 protons, 2 neutrons, and no electrons. And so its mass is about 6.4. We're going to use approximately 6.4 times 10 to the minus 27 kilograms. That's its mass. And what we want to find now is the velocity that it has, its average velocity. If you have a collection of helium molecules out in space, and you have helium and hydrogen gas clouds in space, what is their average velocity given this temperature? And we have a result out of statistical mechanics that gives us a relationship between the average kinetic energy of a group of particles in space and the temperature, where K sub B is something called the Boltzmann constant. Again, it's something that comes out of statistical physics. It's a value that I don't remember that one off the top of my head, but I think I have it noted here.
Okay, so
Is 3/2 part of the formula?
3/2 is part of the formula. Yeah, it's on one side 1/2, the other side 3/2.
She gave us it already.
I'm looking for the value of that Boltzmann constant, K sub B. Does somebody have it from the notes?
Of what?
I think I'm just about to locate it here.
Then you don't phase it.
Right, I can't believe I don't have that. Oh, wait, okay, no, it's actually, that was Stefan Boltzmann constant. This is another constant. It's 1.38 times 10 to the negative 23. So it's, we have 1.38 times 10 to the negative 23. And I'll provide this for you as well, and that's in terms of joules per Kelvin. Again, it's a result that comes out of statistical physics working with gigantic numbers of small particles. Okay, so we're looking for the velocity, so we can just solve for velocity. So v squared is equal to 2m times 3/2 K sub B t.
Is that a B or a D?
B.
That is B.
And so if we, you can take the positive square root of all of this, and we're going to have the average velocity that the helium atoms will have in like, say, a helium cloud in space that's at the background temperature. So we can put everything in. So we have 3 times
Okay.
1.38 times 10 to the minus 23 times 3.5 Kelvin all over 6.4 times 10 to the minus 27. And that's going to get us a relatively small number compared to how fast these things can travel when they get up. Okay, does somebody have a result for this? Okay, on the inside I'm getting inside the square root, I'm getting about 2.26 times 10 to the minus 23 minus 27. So we have 2.26 times really 10 to the 4, but that's square rooted. So let's get something out of this. And I'm getting about 150.3 meters per second. So very small compared to the speed of light, but if you were going that fast in a car, I don't think you could survive that. What, about 6 meters per second? I don't think the car could survive that. Over the weekend I saw a dragster try to go 300 miles per hour, and it's about 6 meters per second is roughly 50 or 60 miles per hour. So they were going roughly 30 meters per second, and the car just flew apart. So even though this is very slow compared to what light speed is in space, it's still very large compared to things that velocities that we're accustomed to having. Okay, so questions about 9. Again, 9 is one of those questions that we're going to have about 3 pretty much direct calculation questions and 3 that are a little bit less direct. Okay. Okay, so question 10, we're looking at a car going around an embankment, or first not an embankment. We're going to rely on friction, static friction, to keep the car from spinning off out of control. And in the second part, we're going to look at how to accomplish the same thing without the use of friction.
With friction.
Okay, so it's going to be the static friction in this case. So I gave a roadway that has a radius of curvature of about 20 meters, and I said we have a mu sub s value, the coefficient of static friction on average between the car's tires and the roadway, about 0.3. And we want to know how fast can the car take this turn without sliding. Something has to give it centripetal, in other words, something has to oppose its tendency to slide around the curve, and so we're going to have the inward force of static friction. It's going to be directed that way, and that's going to be our centripetal force, keeping it moving in a centered direction. And we derived an expression for the center-seeking force as mv squared r. We derived centripetal acceleration, and that in this case is provided by the maximum value of static friction, or by the force of static friction. But we want to push this thing to the limit, so we're going to go for the maximum value of the force of static friction. This maximum value is mu sub s times the normal force, that is the normal force on the surface, which in this case we don't have an embankment, so it's mg cosine of the angle is equal to mv squared over 2. That we need to know how fast this car can go and still have friction provide enough force to keep it from sliding off, so we can cancel out the m's, and we get v squared is equal to 2 u sub s g cosine of the angle. But the angle actually, there isn't an angle here.
Is it 2 or 20?
I think I said 20, yeah. 2 would be a very...
You put
Oh,
mv
you
squared
know
over
what?
2, is that over 20?
Well, it's mv squared over 2.
Oh, okay. But
Right.
it's in radius,
Oh,
over
no,
radius.
you're right, actually. Somehow I started thinking about kinetic energy and replaced the 2 with the 20 with a 2. So let's keep it all symbolic now and solve for it symbolically. So we have, thank you, that's a definite oversight. mg cosine of the angle. Remember, the angle is the incline of the surface, but this angle here is 0 degrees because it's a flat road, and cosine of 0 degrees, that's 1. So we have, this is our value.
I thought you got rid of m.
We did get rid of m, and oddly enough, it doesn't depend on m, which you would think that, say, a heavy truck going on a road would be able to go faster in terms of friction because it's so much heavier. But if that indeed was the same coefficient of friction for it, then the mass would have no difference. It would make no difference.
Really quick, would you be able to cross out the m over here on the mv squared?
In fact, we have to cross it out. Cross out one
Yeah,
side,
and also on the v squared at the top.
Yeah, I need to do all of that, thank you.
That way we
It's a lot of small mistakes here
Thank
that
you.
are so easy to make sometimes. Okay, let's then solve for this. And so we have 20 times 0.3 times 10. So we have the square root of 60, so what about that?
7.75.
Yeah, not quite 8, greater than 7. 7.75 meters per second. That's our v value.
Is that all we're
Okay, so that's how fast you can go around this curve
And be okay.
and be okay, yeah.
Not die.
But next we want to find out,
But in real life, no.
yeah, with an embankment, because but because
That was all one question that she had.
That was the first part.
Oh yeah, now we gotta
sorry,
answer
yeah,
B.
let me get over here.
Thank you.
Okay.
If you wanted to,
One thing that's important to do when you design roads like this, not that I've ever designed them, but you don't want to rely on friction to be the only factor keeping the car on the road. Different cars have different types of tires, different weather conditions will change the coefficient of friction. So what you want to do is ideally have the reliance be on the banking angle of the curve instead of on friction. And so we did this 3 different ways in class. One way we did it relying only on friction. One way we did it relying only on the banking angle, but there was still friction in that case. And in the other case, we did it just relying on both, which is a more complicated case. Okay, I want to make sure I don't make a mistake with this one here.
where I started at.
Okay, so let's take a look at what we have when we have a banking angle involved.
When I started taking pictures, it just happened to be in my.
In other words, we're going to bank the roadway. We're
That's
still going to
amazing.
have
Come
the
on.
same radius of curvature out to the center, and our center-seeking force has to still be the force in that direction. But now we have to look at something else to provide that force, since we're not going to rely on the force of static friction. So we have to look at what forces are acting on the car, and really they have to rely on the force of gravity. So if you look at the normal force, the force that's perpendicular with respect to the surface, if we break down gravity into its 2 components,
Oh wait, this is part 2. Check it.
Yeah.
okay, so we're going to have a normal force, and this is our normal force. Actually, that's not, that's F sub t. Normal force I've been do them like this, it's going to have a y component, and it's going to have an x component. It's only the x component that is going in the appropriate direction to give the center-seeking force. So we're going to have our force, mv squared over r, is going to equal the normal component, the x component of the normal force acting on the vehicle. And we said that the normal force is given by mg cosine of the angle. We also showed, I showed it, in fact I can show it quickly again, that these two angles are synonymous. I won't go through the whole derivation. I have it, it's in our notes, but
So we find that angle, and we know the angle of the incline.
yeah.
How are those two angles the same?
Okay, if you look at this, if you call this angle A,
That
geometrically this angle is also angle A. The three of these have to sum to 180, which means the two of these have to sum to 90. And this one sums to 90 with the one that's to make the perpendicular line right here. So the two of them are going to be equal.
Makes sense.
Okay, so we have that angle. I'm trying to. So something's bothering me about. Okay.
No, it's got something.
I feel like I'm leaving something out. Sometimes I stumble over this one when I give it, and I thought I had it really well done in my notes. I'm not finding the section where I gave this.
You just left this one on the task.
Oh, no, this is a really good one.
Wait, this is part B of the,
Yeah, this is part B. Should be part B.
Oh, no, in fact, okay, I have it here again. I just needed to kind of recover it.
Yeah, f of y is cosine.
Right, so what we have here, okay, so this angle we have here, if you look at the forces acting on something about this bothers me. I mean, I know what to present here, but still something about it is giving me a little bit of a pause
Human
here.
zoom. The human zoom.
Okay, let's look at these forces here. If we look at the forces acting on this, the y component of the normal force is exactly
Mg
counteracts
sine.
gravity.
Sine.
So we have this component of the normal force, it counteracts gravity. So we know that it's equal to mg. And we know also that this will be, we can do our sine and cosine. We can come out with the angle here. This is our kind of taking this triangle and turning it on its side so we can see it better. We have this, so we have sine of that angle is the opposite over the hypotenuse. So we end up having this as our value. Okay, so what we have is the normal force times the sine of the angle is equal to mv squared over r. We don't know the normal force in this case, but we do know that the y component of the normal force exactly counterbalances gravity.
So
And that y component likewise is given by normal force cosine of the angle. That's equal to mg. So that means that the normal force is going to equal to mg cosine of the angle. So what that tells us, if we take this and substitute it back in, we get, on one side, we get mg over cosine of the angle times sine of the angle.
Or mg.
On the other side is equal to exactly mv squared over r. We're looking for, in this case, we're looking for the angle. So we know what v is. So let's solve for the angle if we can. And we can do it. We can cancel this. We end up with an expression that has two trig functions in it. But if you remember what the trig functions, how they're defined, this is the opposite over the hypotenuse. This is the adjacent over the hypotenuse, which means we have the opposite over the hypotenuse over the adjacent over the hypotenuse. Well, there's a hypotenuse that's just asking for it there.
We're missing the g.
Oh, she's explaining.
On the right side.
Okay, yeah, in fact, let's put the g in there so I don't forget to put it back in. And so what this is opposite over adjacent, which is the tangent. So now we have one function that has the angle in it. So we have, we can rewrite this.
The tangent of theta.
Sorry, tangent of the angle
G.
times g is equal to v squared over r. So if we get the tangent of the angle, it's equal to v squared r over g, r times g. We can take the inverse tangent of both sides, and that's going to get the angle that we're going to have to make this thing in order to give it the same capacity to go just as fast as it did when we relied on the coefficient of static friction instead. R is still 20, yeah, we're keeping exactly the same, but we're just trying to see how you can create the same effect if you don't rely on friction. Okay, so 7.75 squared over 20 times 10, and that's going to give us hopefully not too large of an angle that would be impossible to drive on. And I suspect that, in fact, I know that it's not going to be. In fact, about 16.7. So about 16.7 degrees, you're going to have the same effect as if you had a coefficient of static friction of 0.3. On such a curve, unless it was made of ice or some really slick surface, you would indeed be able to go faster than that because you have the coefficient of static friction providing a frictional force, and we did a derivation with that as well, and it's a more involved expression, but you're going to be able to go faster in actuality, but this is just if you're going to rely only on the banking angle and the component of the normal force that it gives to provide that centripetal acceleration. Okay, questions about this one? Okay, what I'd like to look at then is the next one, which okay. Question 11 is not a bad question, but to really be able to, and we could solve it, it's a very quick, easy one to solve. I don't feel like I've given enough background information, enough background development on certain types of things that are called pseudo-forces, like Coriolis forces, centrifugal forces, centripetal forces, to really do justice to this problem. Its solution is just a very quick, maybe one or two lines. That the idea with that, the giant space wheel was that as the wheel turns around, it's giving a centripetal acceleration to the surface, every point on the surface of the wheel. You have a reaction force, forces coming in pairs, that's going to kind of, in effect, keep you glued to it gravitationally. And it turns out that the mass of the person doesn't have an effect with this one. It's very different from the ride where you had to counteract the downward force of gravity. The only thing that matters in this really is the how fast the wheel is spinning. But I'm going to take this one out of the test right here. Yay! I wish I'd given, I want to do it more justice whenever I present it next time to the next class that comes through, but I don't think we have enough time to do this one justice here. Okay, the last one is one that looks like it's more difficult than it is maybe, that it's a problem in the conservation of momentum, and it's going to be one of those that's one of the more quick ones to solve. Okay, so the last of the new questions, 11/12. We have a spinning disc, and we have a certain mass that initially
Since we
is
took out
off
11,
of
it's
the
11
spinning
now.
disc. And the disc is spinning
It used to be
initially
12, but now it's
at
11.
a rate of 10 radians per second. And we have an 80 centimeter radius
So this is the
for the disc. And at some point, we're going to take a small mass and put it on the disc.
scribbled it down
I also
last.
gave a mass for the, in fact, I hope I gave a mass for the, yeah, in fact, I did give a 10 kilogram mass. This was at some initial time, so we'll call this our initial omega. At some later time, we place the mass on the disc. We place it at a point that's 30 centimeters from the center of the disc, and it begins rotating with the disc with the same velocity. And so our question is going to be, what is the final velocity, angular velocity that they spin with? And I also gave you a value for the mass, which I gave as a 1.2 kilogram mass. And so we're going to see how that changes the angular velocity of the system. The idea is that the total angular momentum of the system is constant.
The hands are
And
really
so
cool.
we have the initial is equal to the final, and this is the angular momentum, which we said is given by I omega. That was our angular momentum equation. And initially, the only thing that has an omega is the disk. And so initially we have I for the disk times omega initial plus I, we'll call I for the mass, times 0. That's our initial angular momentum. On the other side, we have the two combined, moving with the common angular velocity, and we end up with an expression that looks like this. Okay. Whatever type of shape I give you, you're going to have to, I have to give you a moment of inertia, an I value that can go with it, and I'll do that. In this case, I gave you that the value for the moment of inertia for the spinning disk, this was mr squared over 2, and I gave you the value for any individual mass at a distance r away from where it was spinning was equal to mr squared. So if we combine these, what we're solving for, this is what we need, the omega f. So let's solve for it symbolically and then start putting in values that will give us the correct answer. Okay, so we divide both sides by that sum of the moments of inertia, and we end up getting, and let me make that more clear, I sub d. And that's just the moment of inertia for the spinning disk. And on the bottom we have I sub d plus I for the mass.
Isn't it I sub d omega I plus IM?
It is, except that initially the mass is just sitting there. It has no angular velocity.
So it doesn't matter.
It doesn't have an effect on this one, right? Because we're looking at the total system, and its contribution initially was nothing. Okay, so we have mr squared over 2. Okay, so that's 10. We're going to convert the radius of the disk to meters, so it's 0.8. We square that, divide by 2, and we have 10. So again, we've converted meters to centimeters to meters, and on the bottom we have 10 over 2.8 squared. And then the mass itself that we've added to it has a mass of 1.2 kilograms, and it's at a radial distance r from where it's rotating, a radial distance r of 0.3 meters, and we square that. Okay, so we can start simplifying some things here. So now we have 50 times 0.64 on top, and 5 times 0.64 on the bottom, plus 1.2 times is at 0.09. And now it's just a matter of working the numbers out here.
Why is it 50 times 0.64?
Okay, I skipped some steps, but that would be 5. 5 times 10 would be the 50.
Got it.
And then 0.8 times 0.8 is the 0.64. And the same thing on the bottom, except that it's 5 rather than 50 on the bottom. Okay. Okay, so we have 32 over 3.2 plus 1.2 times 0.09. And that's 0.108. So we have 32 over 3.308. A little bit less than 10. And we'll find out how much less, about 9.67. So it's slowing it down a little bit, 9.67 radians per second. And so this one's going to be another one that will be a very quick and easy one to get credit for. And that's it for this one. That's how a lot of the questions are at the last part of the physics course. Frequently, you have a lot of very good short calculations that just still illustrate some ideas. Okay, questions now about these now 11 that are candidates for the 6 problems on the test that deal with exam 4. Okay, do we have any requests for problems to see solved out of the previous sections? We have roughly half an hour where we can solve problems. So if anybody has any special requests out of...
Were you going to cancel any out of the 2 or 3 reviews?
Because you canceled one out of the first one.
You canceled one out of the 4th one.
Right.
So are you going to cancel any out of the 2 or 3?
No, because I thought about that. I gave fewer for that, and no, I think those are all. The other ones are going to stay. I just given so many kind of overload of projectiles in the first one, and I hadn't done justice to the other ones. No, the others are kind of, well, they're all possibilities. Okay. So look over sets 2 and 3 for the final, and yeah.
For set 3?
Set 3, number 3, the pendulum problem. Okay, let's take a look at that one then. And then anyone else who wants one, have it ready to request, so that since we're not going to have time to solve every one of them. Okay. Okay, this one mirrors one that we did in the lab, the ballistic pendulum problem, where we fired a projectile at a pendulum, and it sets it in motion, and I say how high it moves it. So, in fact, let me erase all of this once we have the whole board work with. Well, in fact, we have the entire board. This hasn't been clear since the start of the semester. Okay, so we had a mass of the pendulum that was hanging here initially. We fire a projectile that we call mass 1. I'm calling this the velocity of the ball of the projectile before they hit. In the problem, I actually called it V0. So I'll keep my notation the same as I gave it with. And I'm saying that initially this thing wasn't moving. Okay, at some point they collide, and so they collide, they're together, they move with a common velocity, and then a little bit later, their center of mass has raised by a distance, just like it was in the lab, except that this has gone up 8 centimeters. And we know about, so this was set 3, problem 3. And we had the mass of the projectile being 2 grams. And we had the mass of the pendulum at about 300 grams. And the problem was to find V0 and the velocity to move with together. And so I'll kind of refer to this as 1, 2, and 3 at 3 different times. Before they collide, they have a common velocity to move with together, and they move up as high as they go before coming back down, but they're still together right here. So it's one that we've solved before, and we can solve it again. Our two relationships we're going to work with here, the first one is that the momentum before is equal to the momentum after from 1 to 2, and then from 2 to 3, we're going to have the energy before is equal to the energy at stage 3. So if we look at from 1 to 2, we have momentum conservation. And unfortunately, we're using an overworked letter P again.
Yeah.
And so this is the momentum before, and so this is really going from 1 to 2.
Appreciate it.
And so in 1 we have M1 times V0 plus M2 times 0. It's not moving. We have the total momentum of the system. Our system consists of M1 and M2 on the one side. On the other we have M2, well, they're moving with a common velocity, so we have M1 plus M2 times their common velocity. Well, we have two unknowns. They both appear here. Let's solve this in terms of one of our unknowns. We have M1 V0 is equal to M1 plus M2 VT. So we solve for one unknown in terms of the other. So we have one equation, but we still have two unknowns. So we know the masses. We don't have to convert them because they're both in grams, so the grams here will cancel out the grams here. Let's make this completely into a numerical statement as much as we can. So we can do 2 plus 300 over 2 VT. So we have 302 divided by 2 VT. So that gives us 151 VT is equal to V0. And the second equation, when we go from point 2 to point 3, we're going to use the fact that the energy is approximately conserved. In other words, we're going to translate that kinetic energy into potential energy. So we're going to have the kinetic energy at the first is going to equal to the potential energy final. I showed some more of the details of this in class, but and showed how we got to this point. But it ends up that our change in potential energy is equal to the initial kinetic energy.
Just one.
I think we showed the full derivation of that before, so we'll do M1 plus M2
411
VT squared
at gmail.com.
over 2. That's what its energy, its kinetic energy at point 2. And the final time is become M1 plus M2 times G times the change in height, which that's our 8 centimeters. Well, what's nice is we can cancel out the masses on both sides. We have VT squared over 2 is equal to G, and we're going to convert this over to 0.08, because this is in terms of meters per second squared, so we have to make our conversion. So we do centimeters to meters, and that's what we have right here. Okay, so we do 10 times 0.08 VT squared over 2. So, well, let's just get this VT squared is equal to 2 times 10 times 0.08. So VT is equal to the square root of 1.6. So VT, we're going to have one of our equations, or one of our values out of this now. So we get about 1.26. So 1.26 meters per second for our VT. And then we get going back to our initial equation, we have 151 times 1.26 is equal to the initial velocity of this projectile in the problem. And so we get about 190.26 meters per second. And that's how we do this one. We do the momentum being constant from part 1 to part 2. We rely on that equation, and we rely on that relationship of the kinetic energy getting poured into a change in potential energy for from 2 to 3. Okay, so that's another one of the problems. Does anybody have a request, a specific request for another one of the problems in here? And if you wanted to look at your notes, if there was one that would, okay.
Number 5 on that same set of
Okay.
questions.
Okay, number 5 on set 3. I don't have a number 5. I'm not.
It's the,
Is that the bouncing ball?
no, it's
Oh, okay.
There's a string,
the spring, yeah.
Oh, okay. Let me see. If you'll show it to me. Is that where I have? Oh, okay. I think I'm seeing
Got
it
it.
here.
It's at the very bottom and then it curves
Okay, no, I
upward.
do see it here. Okay, yeah. Let's take a look at this one then. That's a good question, and there's a very good chance that one's going to make it on the exam.
what?
So, what I give you, I give you a graph, and I ask you to find several things from the graph to extract the information of the graph from the graph. And so we have a spring mass system that's showing harmonic motion. We have 6 centimeters up here, and so it oscillates between 6 and minus 6. Its initial position is, so it looks something like this, except that I give you values for T1 and T2. I tell you that T1 is equal to 0.3, and T2 is equal to what did I give for T2? I give some values for it.
T2 minus T1
Yeah, that's what you.
Okay, so
You just
I
didn't wanna
give
go on to the next
0.5
page.
maybe for that.
It also goes like.
Okay, so I give you a value for the spring constant, and I ask you to find several things. Okay, so I give you a K value, and this is number 5 on the section 3. Okay, so I give you a K value of 50 newtons per meter. And I ask you to find the general equation as well as the kinetic energy at positive 4 centimeters and the acceleration. Okay, so 3 things you're looking for here, and we'll take them all in turn. So the first one is x of t in general, and then the second one is the velocity at 4 centimeters, and then we want a specific value of the acceleration at 4 centimeters. Okay, the x of t position equation has this form, a cosine omega t plus some phase angle, and so we need all 3 of these things here. This is how far back and forth it goes. Its maximum displacement, it goes back and forth between 6 and minus 6, so this is just 6.
Because it's the whole number divided by 2, right?
The whole distance divided by 2,
Yeah,
or
okay.
if you if how this looks, if this is a spring, a mass in a spring, if this is x0, this distance here would be a, and this would be minus a, and it's going to oscillate back and forth between those 2
Okay.
points. And so this isn't drawn proportionally, but
We get that. Yeah.
right,
We get that.
right. And then we have 2 pi over the period for this, so we have to get the period. But I tell you that what these 2 values are, and you know that T2 minus T1 is equal to 0.2, and that's 1/4 segment. And we said that 4 4 of those will make up the period. Each one of these segments is an equal time period. So t would be 4 times 0.2. So we have 2 pi, and that's going to be 0.8. So we have 2 pi over 0.8. And again, this is our t value that we've gotten over here. And so that's going to be what, 2.5 pi. So we have everything we need except for the phase angle. That's going to be a little bit trickier to get. The first thing we want to do is to okay, so we have that. Let's begin the phase angle. Remember, what we have to do here is we have to we do 2 things. We see, if this is just cosine as a function of the angle, it gets to this part 2 different times. We have to find the second time it gets to that point. I'm kind of belaboring how
Isn't that just 3 pi, 3 half pi? So 3 pi over 2?
well, let's solve for it. So we have the cosine. I know there's a definite trig relationship between these 2 points. The idea here is, though, that you would find its value at 0, which is, I gave as minus 4.5. And so, to find the phase angle, you do x at 0 is equal to minus 4.5, and that's equal to 6 cosine omega times 0 plus the phase angle. So, that's just 0. So you have minus, about minus 0.75, minus 0.75 is equal to the cosine of the phase angle. So if you take the inverse cosine of that, you're going to get an angle, but it's going to be off by a little bit because you want it the second time it gets there. And that's something, okay, so we get the cosine of minus 0.75.
The inverse cosine.
Yeah, the inverse cosine, I'm getting about 138 degrees. I need to convert that over to radians.
Multiply by pi over 180.
Right, but pi over 180. But the situation is, this is for the first time it gets there. We need it the second time it gets there. That's something I'm rusty on how you find that second value. It gets there twice.
It's going to be the
But
same.
I said the phase angle is just where it starts compared to the original cosine graph.
It starts at this point on the graph, and so it doesn't start here. It starts here on the graph, so it's going to be.
That would just be quarter pi, half pi, 3 halves pi, right?
Is every point separated by a quarter pi? Is that?
Yeah.
Okay, that's one thing okay, so it's
Well,
plus.
I think so, yeah. Because I remember that's how you showed us.
Well, I think that's not completely correct because right here
That
to here
was-
is not a quarter pi.
So it doesn't start at negative 6 centimeters or somewhere.
Right, it starts at minus 4.5.
Oh, okay. I get.
Right, so
Oh, okay,
I mean,
okay.
it's not going to be exactly quarter pi.
So it doesn't start at. So that's only when it starts at like negative 6.
Right. But because I don't have I know we could find how to do that. I'm belaboring on how would you get the second value of it. I'm rusty with that part of my trig. I think that I'm going to give it to you so that it's going to encounter the first time. We're not going to do the second time because I haven't talked about how to do that. And so I'll give it to where it would have been 138 degrees, and I'm going to have it the first time it gets there rather than the second time.
So to get it to where it's at the second time, you multiply by 2?
No, I don't think it's that easy. I know there's a definite relationship, but I don't remember what it is out of the trig to get the second time it gets there. Because it's the identical value. And I don't want to take any more of the review time for that, so I'm going to give you one where it gets there the first time, so if you take the inverse cosine, you'll get the angle. I'll give you that one when it's in the first half of the cycle. And so this you would have to also convert to radians. And so we said
Multiply by pi over 180.
It's 2 pi over 360 or pi over 180, the same thing. And this will get us the value in radians. And so this isn't exactly the angle. It would be if it started right here. I'm sorry, if it started right there, but it was going down and then went back up. That's what we're actually solving for it the first time, which is okay. I'm going to give you one for the first time it gets there only. And when I teach the class again, I'm going to have it a method better worked out for that. Okay, so we have 0.77 pi, and we'll keep that as our value of the angle, a phase angle in radians. Okay. Okay, so let's get, so what we have, again, we've changed the graph a little bit. We have 6 cosine and an omega. The omega value we said is 2.5 pi times t plus 0.077 pi. And again, that's for a graph that looks like, instead of that one, it looks like this. So we've modified the graph a little bit. Okay, so that's the first part. Now the second part, we want our velocity when it's at 4 centimeters, at positive 4 centimeters. I would have to say whether, I think I asked for the, no, a kinetic energy, not the velocity. So the kinetic energy is still mv squared over 2. That's still our kinetic energy. We don't have a mass given to us, but we know that omega is equal to the square root of k over m. That's an equation that we derived and that we showed, and we can use this now. And we know that omega itself is equal to 2.5 pi. And we know what k is equal to. We said k for this one was 50, so we have omega squared would be 50 over m, and that's equal to 2.5 pi squared. So on the one side we have 6.25 pi squared, 50 over m. So we have 50 divided by 6.25 pi squared. That's equal to our mass value. We want the total kinetic energy, so we're going to have to, so we have that value for mass. Let's go ahead and quickly calculate it so that we can use it, because it's going to be used in a lot of the problem to come. Okay, so I'm getting about 0.81 kilograms. So it's a pretty hefty mass. Okay, so our kinetic energy then would be 0.81 over 2 v squared. So we need our v. We have one expression for v was k over m, a squared minus x squared. V squared is just k m a squared minus x squared. So our kinetic energy turns out to be, we could simplify it, mv squared over 2. So we have m times k a squared minus x squared over m times 2. So our mass effectively cancels out for this. If we have mv squared, if v squared is k over m, we have k over m, a squared minus x squared. So we're gonna need the mass for the acceleration, but we could solve this without even knowing the mass, because oddly enough, the mass doesn't play a role in the kinetic energy in this case, due to the nature of the acceleration. So we can calculate the whole thing as 50, and then A is 0.06, and square it. X is 0.04, and we square it. And again, this is centimeters to meters, because we want to have joules of energy, which is newtons times meters. And all of that's divided by 2. We're going to actually have to have that mass for the next part that we do. Okay, so let's get this first part solved. I'm getting about 0.05 joules, so not a lot of kinetic energy, but that's the result we have. And then finally, we have, remember we had the force was equal to minus kx, and it's equal to m times a. So we had a is equal to minus kx over m. And now here's where that mass is going to come in really handy that we've calculated, because we have to have it here. We could get by without it over here if we work this out all the way this way. But we have to have it here. So we have minus 50 times 4 over 0.81. So this is going to be negative. It's directed back towards the center of equilibrium for the spring. It has a really large acceleration of about minus 247 meters per second squared. And so that's our acceleration in this instant. Okay, questions about this problem here? Again, the part that was a little bit shaky was the phase angle, but I'm going to have it so that you get the first time it gets there and not the second. We're not going to be concerned with that. And so you just find that's your time 0 for your position equation. Okay, questions or requests? Okay.
I got one more.
Oh yeah, go ahead.
For set 3, number 2, like the one we have to find, where it's like.
Set 3, number 2?
Yes.
Okay, yeah, the equilibrium question. Okay, well, let's look at that one. We have a setup that, the system is in equilibrium, and we have to find one of the unknown forces. Okay, so it was the second of the equilibrium type problems. And we had a beam at an angle that's going to, we had a system set up so that this angle here is 70 degrees. If you look at the top of this, the angle that this string is set up with is at 230 degrees to a positive x-axis centered there, and we have a hanging mass. And we have the mass is 10 kilograms. And I labeled some of the forces. I actually labeled this one, there's going to be a tension or a force in this string, and that's the force that we want to find. Okay, so we're going to find F1 in polar form, so we have to have its magnitude and its angle.
So 230, is that to the string or to the?
Oh, it's 230 to the string. And so that's also the direction of the force in the string, or the tension in the string. That's the angle that it's going to be directed as well. Okay, so here we have to do the sum of the forces in the x direction go to 0, and the sum of the forces in the y direction go to 0. And in the y direction, well, let's label the force here. This thing's pushing out as F2. So we have F1, F2, and we'll call the force of gravity, we'll call that one F3. And so in the x direction, if we break it down, we have F2 that's going up like this. It has an F2x and an F2y. F1's pulling back this way, so F1 has an F1y and an F2 and an F1x. And of course, F3 is all in the y direction. So if we look at this, we can say, okay, we have two equations we can come up with. We have F2x plus F1x goes to 0, and we have F2, there are no other forces in the x direction. But the sign will be taken care of when we use the appropriate angle. Their magnitudes are going to cancel each other out, but the sign will be taken care of when we use the angle of 230 degrees. And so that's some of the forces in the x direction. In the y direction, we have F1y plus F2y plus F3 is 0. And we're going to use these equations to solve for our unknown, which we need F1x. We need F1. And so if we flesh out these equations, we have F2x is going to equal to F2, and that's going to be cosine of 70 degrees. F1x is equal to F1 cosine of 230. That's going to give us the minus sign. And so what we have for, and we'll call this one equation 1, and this one equation 2. So we have F1 cosine of 230 degrees plus F2 cosine of 70 degrees goes to 0. Let's solve for F1 in terms of F2. Or rather, let's solve for F2 in terms of F1. So we have minus F1 cosine of 230 degrees divided by the cosine of 70 degrees. So we're getting close. We're solving for this in terms of F2 so that we can substitute that into our next equation and be able to solve for F1 directly. Okay, so we have cosine of 230 divided by cosine of 70, and so we get that F2 is equal to minus 1.88 F1, and that's the same as 1.88 F1 without the minus sign. So that's one of our equations, and we're going to be able to use this when we set up our second equation in just a moment. So that's one of our important relationships. The next one, we're going to work with equation 2. And so equation 2, what that becomes is F1 sine of 230 degrees plus F2 sine of 70 degrees plus F3 sine of 270 degrees. Well, this is just minus 1, and this is mass times gravity. So we have minus mass times gravity, so we have minus 10 times 10, or we have minus 100. And so we end up with is F1 sine of 230 degrees plus F2 sine of 70 degrees minus 100 is equal to 0. Well, let's work with this a little bit more. F1 sine of 230 degrees plus F2 sine of 70 degrees is equal to 100. That we have a relationship between F2 and F1, and we can use that to put this totally in terms of F1 so we can solve for F1. So we have F1 sine of 230 degrees plus F2, which is 1.88 F1 sine of 70 degrees is equal to 100. Well, if you factor out in F1, we have sine of 230 degrees plus 1.88, sine of 70 degrees is equal to 100. Let's evaluate that number in parentheses so we don't have to write it again.
How about F2, it is 1.88 F1?
It is. See, well, F2 is, but then we put it in right here.
Oh, I
The
see.
sign is still there, yeah. And I'm getting, this is right at 1. That's rather odd. So this is right at, it's a little bit less than 1. It's 1.0006. So F1 is going to be just a little bit less than 100. That result is a surprise to me, but it's a valid result. Let me make that 6 more distinct. So I'm getting about 99.94. That's its magnitude. Its direction is another question. So that's how many newtons we have in terms of F1. Its direction, it's directed along the string, which I've already given you is 230 degrees with respect to a positive x-axis as we count things. And so what this gives us is that F1 in polar form would be about 99.94 angled at 230 degrees. Okay, so that's a distinct possibility for the test. Questions about this problem, or are there requests for any other problems? We have a little bit of time left, I think. Actually, we've run out of time. If you have questions, you can email them to me. I can try to help you if you get stuck at a spot that way. Otherwise, I'll see you downstairs on Tuesday at 10 o'clock. Or 10:15, I think it is.